Samuel Willenbring.
I'm Jacob Huseman.
And I'm Josh Huseman.
And we're here to represent North Dakota State University and the 2019 Master Robotic Mining Competition.
Before beginning, we're going to go over the safety plan. First of all, we need to stay at least 5 feet away from the robot at all times. We need to be careful of the sharp edges, and we also need to ensure that we power down the robot prior to performing any troubleshooting.
A little bit about ourselves. We placed second overall at the competition last year, and we are a relatively small team from North Dakota. Some of our performance goals is to reduce the overall robot mass. Last year we weighed 53 kilograms, and this year we weighed 47 kilograms, which is close to our target mass of 45. This last competition we mined just over 1 kilogram of ice, and this year we are targeting 10 kilograms. And we are also aiming to reduce our mining cycle from around 40 seconds to 20 seconds. And electrically,
we're going for complete autonomy. Last year we didn't quite get it, we got half autonomy. We're hoping to reduce our initialization to zig zone time from about 2 minutes to 40 seconds. And we're also hoping to reduce our localization radius from about 30 centimeters to 2.5 centimeters, which allows us to have much tighter control of the robot's path.
Some of our design philosophy is because we have a reduced number count, we need to improve how we manufacture things. So our system manufacturability was reduced, and we also needed to work on our navigation with our robot and maintainability because our subsystems were hard to maintain last year. And besides that, we needed to reduce our things I talked about on the previous slide. Some of the alternative analysis we covered was our frame. So the design began this last summer after the 2018 competition. We looked at a method of anchoring ourselves to the ground so that we could mine deeper. That included incorporating some ground screws into the frame, as you can see up on the far right. And we also considered placement of the central drive unit, which powers our backhoe, as well as some of the vibration analysis we used to filter out our BP1.
For localization, we considered something other than the April tags that we used last year. We were hoping to use the HTC Vive because it's more of a cost solution and be less work and integration for the team. Unfortunately, the HTC Vive uses an IMU pretty heavily in its calculations, and I could not figure out how to remove that. So we ended up going with an April tags based solution again this year. Much improved from last year though.
Alongside the alternative analysis, you can see here our decision matrices. We weighed multiple concepts for each system on the robot. For example, the wheel system, we had our different carbon fiber designs. We really cared about how lightweight, manufacturable, and easy to build it was, along with how cheap to build it was. So that's how we picked our final design. And then we also weighed multiple concepts for what we call our central drive on our robot, which drives most of the mining cycle. And we care about basically the same criteria there as well.
For new design elements electrically, we improved our autonomy system, our localization, our drive controller, and our dig controller, along with a few smaller subsystems. For autonomy, our high-level autonomy consists of a finite state machine that basically maps out the different states we believe the robot can enter, and how to handle each one, and how to enter other states based off of that. For pathfinding, we were originally going with a Bezier curve-based pathfinder. The idea was to allow the robot to drive smoothly from the initialization stage to the zig zone and back to the hopper. Unfortunately, we did not have enough time to complete it, so we went with a much more simple turn in place and drive straight forward technique. For localization, we have a dramatic step up from last year with a global shutter camera. We upgraded from the April tags 2 library to the April tags 3 library, and we also have a custom stepper controller that follows the April tags. The data coming from the April tags 3 library goes into the baited filter, which also integrates in some IMU data and a kinematic model of the robot. For the drive controller, like I said before, we were planning on using Bezier curves, but given time constraints, we are going with the turn in place and drive straight forward technique. Our controls consist of a few fault recovery routines, and the rest of it was for Bezier curves, which we are no longer doing. Our dig controller consists of another finite state machine that discretizes the angles and placement of the backhoe, central drive, and bucket, and then figures out where the different components need to be at different times in order to do a complete dig cycle. Our motor controllers for the central drive and the backhoe, each one has a custom firmware that I wrote to integrate some additional features.
Alright, so now I'll just quickly talk about some of the major design elements for our robot this year. So first up, we'll talk about the frame. As you can see on the robot, there's a lot of different systems going on in there, and we have to make sure that all of them are perfectly integrated. So basically we wanted to make sure that the wheels weren't gonna mess with the bag, our ballast bags, which we're using for weighing ourselves down better for mining. With our ballast, we'd have about 110 pounds of digging force. We also changed up our mining cycle a little bit this year. So basically the entire mining cycle is driven off of just two actuators. One's what we call the central drive, and the other is our linear actuator on our backhoe. And so all those different elements are coupled together with linkages, and so our frame has to be stiff enough to counteract all our linkage forces and make sure that everything is perfectly integrated and in the spot it needs to be. So Jacob is going to fire up the robot to demonstrate our regolith deposition system. So first our backhoe will go down. It's always coupled to that central drive that I was talking about. Then that linear actuator will engage to actuate our backhoe bucket. Once that's fully curled, we'll lift the entire backhoe arm up. And there's an intermittent gear inside that central drive that will engage a pair of flaps, and then the backhoe will dump onto them by uncurling the bucket. And then you continue lifting the backhoe, the intermittent gear will finish lifting up those flaps. And then there was also supposed to be a third system, the bucket, coupled into it, but here we'll have it driven by an actuator instead. So we'll dump all of our material using that linear actuator to lift up the bucket. And all the material will be sifted out, so the finer particles that aren't worth any points will fall into the bag to be used for ballast, and gravel will be kept in that bucket and be deposited into the hopper.
The last element of our robot is turning. Each drivetrain is independently driven, so we can skid steer the robot as shown now. And that summarizes the mechanical elements of this robot.
Just a little more in-depth on the design of our wheels and drivetrains. So our wheels are a pre-preg carbon fiber design. One of our members here designed the wheels, and everything was manufactured in-house. We made all our own forms and all our own parts, CNC'd our own hubs, and overall it resulted in a savings of about 1.5 pounds per wheel. And then driving those wheels, we have our planetary drivetrains, which is all manufactured in-house as well. So we have 70 foot-pounds of output torque, which is plenty for anything we need to do for this competition, for whether it's driving over rocks or down into craters or doing a 0-point turn. We can do it with these drivetrains. I'll briefly touch on some of the materials we used. Like I mentioned, in our wheels we utilized pre-impregnated carbon fiber for building them. We did the same thing for our backhoe monoboom, which saved us another 2 pounds. And you can see on there, aluminum is also integrated into the design. And that was supplied from Easy Composites, which is a UK distributor.
Covering budget management, we are mainly split into 4 categories. We have the mechanical team, the electrical team, our outside induced labor, and our travel expenses. This all added up to a budgeted $37,000, and we've used $32,000 as such. Because we incorporated carbon fiber into this year's design, there was a lot more unknown factors that were involved. So a minimum safety factor was established at 1.35 across the board. We fundraised several times throughout the year to help mitigate some of our budget, and that is how we covered that. Going into our schedule management, the only thing we struggled this year was our primary system manufacturing and our secondary system manufacturing, which you can see in the middle of the screen being red. We had a reduced member count this year, so that system those two ended up just going longer than initially expected. Some of our team management, the electrical and software team used GitHub, and the mechanical and manufacturing team used GrabCAD, which enabled us to push and pull models relatively quickly and allows us to lock down models when they're finalized. Our final performance was just demonstrated, and we thank you for watching.